NanoHub U, online instruction.
Welcome back to Unit 1 of our course. This is the 5th lecture. Now, last lecture we talked about how one could make use of this periodicity of a lattice. The fact that you're considering a very long one-dimensional solid, but it's periodic in the sense things look exactly the same anywhere along the chain. You could make use of that to write down the eigenvalues of this n by n matrix, where n can be a huge number, but you can write it down analytically. And you got this EK relation, where for a given k, you could find there is a corresponding E. Now, one point, of course, is not clear, and that is we started with the n by n matrix, which naturally has n discrete eigenvalues. But what we have here is a continuous function. So it looks like I could give you any k and you'd find a corresponding E. So it looks like we got lots of energy eigenvalues instead of just the n that we were looking for. Now, actually the situation is worse. That's because, you see, the equation we got was E equals epsilon plus 2t cosine Ka. And what I had plotted earlier was just the range from minus pi to plus pi. But of course, Ka could keep increasing. You see, it doesn't have to stop at pi. You could go to 2 pi, 3 pi, and so on, right? So, and if you plotted out the cosine function, of course, it would all be periodic. So it is not just that we have an infinite number of eigenvalues of energy we could find here. There's also energy eigenvalues we could find out there, right? But then, at the end of the day, we are looking for n eigenvalues, right? So what we are talking about in this lecture is this rule for counting states, how we extract this discrete number out of this continuous result. So the first point is, of course, why you don't really need to consider anything outside this range of minus pi to plus pi. This range, which is usually called the first Bravais zone. And the reason you do not need to consider anything outside goes something like this. You see, when we derive this dispersion relation, we say that because it's a uniform solid, you could write the wave function at the nth point, nth lattice point, in this form. For a given k, we have a function looking like this. Now, supposing someone says, well, I don't quite like your k, I've got a different k, and it's bigger than yours by 2 pi. So you had a Ka and he has a K prime A, and it's Ka plus 2 pi. Question is, does that represent a new solution? Does that represent a new wave function? And the answer is that, well, corresponding to his K prime, if you calculate the psi n prime, what you'd get is what we had before, and then e to the power I n times 2 pi. That comes from this extra 2 pi, right? So n k prime a is actually n ka plus n times 2 pi. And the point is, since small n is an integer, that quantity is always 1 at all those discrete points of interest. And so psi n prime for every n is equal to psi n. So in other words, this other person, he or she, who came up with a different k, the k prime, is not really describing a new solution. He or she just has a different way of expressing the same thing. It's the same size, you see. What that means is that on this picture, if you have a solution with some k and somebody adds 2 pi to it, that's not a new solution, it's the same one. So you could restrict your attention to a range of 2 pi anywhere on this axis. And the convention is to do it symmetrically around 0. You need not have done that. As I said, a window of 2 pi anywhere would be fine. But what we'll do is take it between minus pi and plus pi. And note that this argument works only because the lattice is discrete. Because we are only interested in the wave functions at these discrete lattice points, at point 1, point 2, point 10, 11, not at 10.7, for example. There's nothing in our model about psi 10.7. Because if there was, then of course, with n equals 10.7, that wouldn't be 1. But because the discrete is lattice, you need to consider k's only in the first Bravin zone. Okay. Now, the next point then is that, okay, we understand that we are restricted to this Bravin zone, but then it still looks like a continuous set of values. How do we extract these n discrete numbers? Now, this is where the periodic boundary condition comes along. And that is that because you are using periodic boundary condition, that is as if this whole thing is in the form of a ring. So, point 1 normally would count to point 0, and point 0 must be the same as point n. So, it's a ring. So, as you go around the ring, what would have been psi 0 should be the same as psi n. But psi n, according to our model, according to our solution, is psi 0 e to the power I n k a. And this condition would be satisfied only for specific values of k, such that, you see, this is psi 0, that's psi 0, which means e to the power I n k a needs to be equal to 1. And that will be true only if n k a is an integer multiple of 2 pi. So that nu stands for some integer. So in other words, only those values of ka should be considered which are integer multiples of 2 pi over n. And now you can see how you get the n discrete eigenvalues, roughly speaking. You see, this range here is 2 pi, and only values of ka that are separated by 2 pi over n are allowed. So it's like there's a point here, another one 2 pi over n, and then 2 times 2 pi over n, and 3 times 2 pi over n. And so the spacing is 2 pi over n, overall thing is 2 pi. So that's how you pick up the n values. So we'll see this with a concrete example. So overall then, the point is the allowed values of ka are integer multiples of 2 pi over n, or you could say the allowed values of k are integer multiples of 2 pi divided by the length of your solid, n times the lattice spacing. Okay. Let's look at a specific example, which is actually also of practical interest, and that is if you had a benzene molecule. Benzene molecule has carbon atoms that are actually arranged in a ring. So here, of course, the periodic boundary condition comes naturally. It's not a matter of convenience here, right? This is benzene ring. So if you wrote out its matrix for something like this, you would have these epsilons down the diagonal, and then this T, T. So, exactly like our 1D solid with periodic boundary conditions. So energy eigenvalues would be given by epsilon plus 2T cosine Ka. But this is a solid of length 6 with periodic boundary conditions. So what that means is the allowed values of Ka will be integer times 2 pi over 6. So that will give you, if you look at the values, so you could put nu equals 0, that would give you that point, minus 1 and plus 1. When it's 1, this is like pi over 3, so it's somewhere there, and then twice that, thrice that, and then you're at the edge of the Bravin zone. Now, if you look at that, you might say, oh, don't you have 7 values there? How did I get the minus 3? Well, it's 2 pi over 6, so in order to get to minus pi, you need minus 3 there, and plus pi is plus 3. And so you might look at that and say, well, you found me 7 eigenvalues. There's supposed to be only 6. Well, the point is minus 3 and plus 3 are really the same. Because remember, the principle is any two values of Ka that are separated by 2 pi, exactly 2 pi, are equivalent. So this is minus pi, that's plus pi. So they're really the same. So you could choose either one, but not both. Now, if you had a solid of length n, then your allowed values would be 2 pi over n times an integer. So you'd run from minus n over 2 to plus n over 2. Now, if n was an even number, let's say 20, then this would be like minus 10 to plus 10, and that would tend to give you 21 values. But the point is, you keep either this one or that one. But then if your n was an odd number, like say 21, then you actually go from -10 to +10, and -10 then is not quite at the edge. It's a little bit inside, because you see n is 21. So when you put 10 there, it doesn't quite give you pi. So it's a little less than the pi. So -10 is here, +10 is over there. So, and then overall you got 21 eigenvalues. So that's how you would get these discrete results, you see, out of this continuous theory that we had done. Right? And those should match exactly what you'd have got if you had just taken the original matrix and numerically solved it. So it's a very powerful method that allows you to write down these eigenvalues of a huge matrix just on a piece of paper. Now, those of you who are familiar with discrete Fourier transforms, they would notice this similarity. You see, in Fourier transforms, usually you have a signal in time and in frequency. Here it is space, z and k. So z and k are kind of like this time and f, t and f. And you see the fact that in z you have a definite range, that's what gives rise to the discreteness in k. So because it's of length, that's the length of your solid, that's what determines the spacing of these points. And the spacing of the lattice here is what determines the range in k. So this Fourier transform relationship, which you may be familiar with if you are familiar with discrete Fourier transforms, so it's kind of similar. On the other hand, if you have never heard of discrete Fourier transforms, don't worry about it. That's just an incidental remark. Okay, so we started with this 1D problem, and we talked about how you could write down the energy eigenvalues of this infinite matrix analytically. What we want to do is now introduce two additional complications so that we can do real solids. And the first one is, instead of a 1D solid, let's think of a 2D or a 3D. So in how to go beyond 1D, that's what we'll do next. Thank you.